Good morning, or at least it's morning for me. Blessings to you wherever you are and whatever time you're listening to this. Today's lesson from section 1.3 and 1.4 is short and pretty easy. The Chinese postman problem deals with the following question. Suppose the postman wants to deliver mail along all streets, and so that's an Euler circuit problem. But maybe the neighborhood looks like this graph here on the left, and if you look at it a bit, you'll notice that vertices B and C are both of odd valence, and so now we know that an Euler circuit isn't possible. But still, it's a valid question to ask, and the postman doesn't want an answer like there is no Euler circuit. He wants an answer, what's the best route? So the numbered arrows propose a possible solution. Go from A to C along edge number 1 and then back to A along edge number 2. Okay, that's unnecessary. He already delivered mail along this road, but you can walk from C to A. And now let's go down to vertex B along edge 3, then 4, 5, 6, and 7. So he has completed a circuit, right? He started at vertex A, he finished at vertex A, and he's walked along every edge, so he was able to successfully deliver the mail. But he backtracked some. He did extra walking. He walked twice along this edge between A and C, and twice along this edge between A and B. So question then, is that the best possible route, or might there be another route with less backtracking? We know there's no route with no backtracking at all because there's no Euler circuit. But would there be a route with less backtracking? Let's see. Suppose he started at vertex A, it doesn't matter, and went to vertex C. There's 1. Then maybe he went over to vertex B. There's 2. And then maybe back to vertex C. There's 3. There's a backtrack. Now maybe 4, 5, and 6. And so if you look at it, he's walked along every edge. So he was able to deliver the mail. He's arrived back at vertex A, so he completed his circuit. And this time there's only one edge that was duplicated, or that he walked along twice. So is the answer shown at the left the best answer? No, because we just found a better one at the right. And then, okay, so now is the answer at the right the best possible answer? Or is there another route that would have even less backtracking than that? I think the answer to that question is no, there's not going to be a better route than this one, because we know there's no Euler circuit at all, and so there's no circuit that will not have any backtracking, and this circuit only has one edge backtrack. So I think the one on the right is probably the best we're going to be able to do. So question, how then can you identify the best possible circuit? That's called a process of Eulerization. If the graph doesn't have an Euler circuit, then we'll modify the graph a little bit so that it does, and then use that new graph that we've created. Step 1, identify the vertices of odd valence. They are, of course, at vertices B and C. Step 2, duplicate chosen edges until, number 1, the graph is connected, and number 2, all vertices have even valence. In other words, we're going to copy certain edges so that the graph does have an Euler circuit. This graph is already connected, so no worries there. And duplicate edges until until all vertices have even valence. Well, how about we take this edge from B to C and we duplicate it? In other words, we'll just put another edge in from B to C like that. And now what about the vertices? A has valence 2, B has valence 4, C has valence 4, D has valence 2. Aha! All even valences. That graph has an Euler circuit. Step 3, Find an Euler circuit for the resulting graph. Well, we added this duplicate edge. Now we know there's an Euler circuit, so let's find it. Say we go 1, 2, 3, 4, 5, and 6. What does that mean then? So here's the picture of what we just did. And what it means is when you go along edge, in this case the edge labeled in blue here, when you go along an edge that you have duplicated, that really means that you go along the original edge and then backtrack. So instead of 2, 3 along separate edges, it's 2, 3 backtrack. But the graph, the modified graph on the left, helped us find out the actual solution to the problem on the right with the backtracking. Let's look at another example. Suppose the directions are to Eulerize this graph. So remember, first step was find vertices of odd valence. And it takes a little looking, but eventually you'll be able to identify that vertices here, say at A and at B, have valence 3, and that those are the only two vertices of odd valence. So now we know we're going to have to duplicate some edges until vertices A and B have even valence. Here's the wrong thing to do. To slip in just a big edge that would go directly from A to B. Why is that wrong? Because we're only allowed to duplicate existing edges. And the reason for that is that a duplicate edge really means a backtrack. So if I say I'm going to add this big edge AB, and then I ask what does that really mean, there's no answer to that. There is no backtracking that can be done along this gigantic edge because there isn't one. So all I can do is duplicate existing edges, and I want to make vertex A have even valence. How about we do this? Let's duplicate that edge. Now A has valence 4, so it's even. But we've messed something else up, right? Now this vertex has valence 5. Before it had even valence, now it has odd valence. Okay, so now we need to add an edge coming into this vertex to make its valence even. Well, let's add this one. And now this has valence 6, so it's even. But we've messed this one up, right? And so now this has valence 5, and we need to add an edge, duplicate an edge that comes in here so that it will end up with even valence. But over here, vertex B also needed a duplicated edge. And so it seems like the right thing to do would be here. And now if you look at it, all vertices, including vertices A and B, have even valence. And so then we could proceed to find an Euler circuit for this graph, which I won't do. Notice that I had some choices here. I mean, I could have, back when I was thinking about vertex A, I could have chosen to duplicate this edge instead. But looking down the road, I knew somehow that I wanted to duplicate an edge coming into A and an edge coming into B, and so it seems to sort of make sense to do what I call daisy chaining, where you go from one vertex of odd valence to another vertex of odd valence and duplicate edges along the way. So, for example, another example, Eulerize this graph so that we could find an Euler circuit for it. And the vertices labeled W, X, Y, and Z are the vertices of odd valence. There are 4 of them. So if we start working, okay, W, and then I need to duplicate an edge coming into W, but eventually I want to duplicate an edge coming into X as well. So how about we do this, and this, and this. Now that fixes the odd valence problem at vertices W and at X. And then vertex y here and vertex z here also need some fixing. And so how about we duplicate this edge and this edge and this edge and this edge, and now vertices y and z also have even valence, and then you could proceed to find an Euler circuit for this graph. Okay, that seems simple enough, but there would have been other ways to do it, right? Here's the same graph as we had before, duplicated 4 times, and we just did an example where we did this duplication. But why did I pick that? Maybe it would be better to duplicate edges and daisy chain from W to Y, and then daisy chain from X to Z, and that would do it as well. Is one of these better than the other? Well, remember we wanted to duplicate the minimum number of edges so that we had as little backtracking as possible. So over here in the first scenario, I duplicated 1, 2, 3, 4, 5, 6, 7 edges. On the second scenario, I duplicated 1, 2, 3, 4, 5, 6, also 7 edges. So it looks like these two are the same, equally good. Or there'd be a possibility maybe I could duplicate like this, going from W to Z, and then daisy chain from X to Y. How about this one? 1, 2, 3, 4, 5, 6, 7, 8, 9. And so this is less than optimal. And there would be other possibilities as well. The question then is it possible to know that you have the best result? In other words, here we've each duplicated 7 edges to get an Eulerization. Could there be an Eulerization with fewer than 7 edges? And we really want to do this type of process in large graphs where there are maybe hundreds or thousands of vertices and edges. That's what an industrial problem or an actual problem in, say, the airline industry would involve. So we really want to, the question really is there a computer program, a computer algorithm that can efficiently solve this problem, can efficiently find out which edges need to be duplicated and then backtracked along as optimally as possible, with as adding or duplicating as few edges as possible. So find a circuit using all edges of a given graph, reusing as few edges as possible. What's the status on this? Has been efficiently solved. One of the things about this class, especially this part of the class, is that we're going to pursue a problem like this for a while, and it'll seem hopefully pretty straightforward. And then along the way I'll make some claim, or the textbook will make some claim, that the answer to this problem is known, and the process or the proof or the solution won't be shown. To prove this and to identify how it is would be well beyond the scope of this course. But it has been solved, and fairly recently solved actually. So your responsibility, your level of responsibility, is to keep track of these various problems as we go through them and note which ones can be easily solved and which ones cannot. Euler circuits, those are easy. We identified a clear algorithm for finding an Euler circuit. The computer has no problem with that. Chinese postman problem, discussing which edges to duplicate, easy. A computer algorithm exists to do that as well. So can be quickly implemented by a computer. On the other hand, some of the related problems that we're about to look at in the next lesson even are examples of situations where computers are not good at doing those problems. No efficient solution is known to exist. Okay, and that is what we have to say about this lesson. Thanks.